Have you ever stopped to think about how we can take the math that's in our heads, the stuff we write on a whiteboard, and actually make a computer understand it? It's a real translation challenge. Today, we're going to learn the grammar of that exact language. Let's dive in.
Seriously, think about that for a second. That tiny little 2 floating up there, you and I know exactly what it means. But to a computer, it's just a character. It's ambiguous. And that's the whole problem we need to solve. How do we make our instructions totally, completely crystal clear? And that's exactly where a tool like Maple comes into the picture. It's way more than just a fancy calculator. Think of it as our mathematical translator. It takes the equations we're familiar with and converts them into a language the computer can execute perfectly every single time.
Okay, so like any language, we've got to start with the alphabet. In Maple, our alphabet is made up of the basic arithmetic operators. These are the absolute building blocks for every single mathematical sentence we're going to write. The good news? Some of this is going to feel super familiar. Addition and subtraction in Maple look exactly like they do in your math notebook. The plus and minus signs are pretty much universal, which is great. That gives us a really solid starting point. All right, here's our first big rule change. In class, we can just write 5x, and everybody knows that means 5 times x, but a computer? It needs you to be explicit. In Maple, you always have to use an asterisk for multiplication. So 5x becomes 5 times x. This is a huge one to remember. And it's a similar story with division. That classic division symbol we all learned in grade school, it gets swapped out for a simple forward slash. So x divided by 4 just becomes x divided by 4. This is actually standard across a ton of programming languages, and it keeps everything looking clean. So, what about that original problem, x squared? Well, this is how Maple solves it, with the caret symbol, that little upward pointing arrow. So x to the power of 2 is written as x caret 2. This simple syntax lets you write out any exponent with perfect clarity, no more ambiguity.
And here it is, all in one spot. This is your essential cheat sheet for speaking basic math to Maple. Plus, minus, asterisk, slash, and caret. It might not seem like much, but with just these 5 operators, you can build an incredible amount of stuff.
Okay, so we've learned the basic words. Now it's time to start putting them together to form complete sentences. And in the world of algebra, one of the most common sentences you'll find is the polynomial. Let's see how we can build one with our new rules. Let's tackle a real-world example. Here's a standard polynomial. I know, it might look a little complicated at first glance, but if we just break it down piece by piece, you'll see it's nothing more than a combination of the rules we literally just covered. Let's just go term by term. First up, x cubed. That's easy. It just becomes x to the third. Next, plus 5x squared becomes plus 5 times x squared. See? We're using both the asterisk and the caret there. Then, plus 11x becomes plus 11 times x. And finally, the constant, plus 50, well, that just stays exactly the same.
And there it is, our final translation. We've taken a standard math expression and turned it into a precise, step-by-step command that the computer can understand perfectly. It's logical, it's clean, and there is zero ambiguity.
So, we've pretty much nailed the basic grammar. But what happens when things get more complex? Well, the language of math is huge, and Maple's vocabulary is built to handle it. Let's take a quick peek at what else is out there.
So yeah, beyond the simple stuff, Maple's language has everything you need for higher-level math. We're talking about all the relational operators, trig functions like sine and cosine, and so much more. Each one has its own specific syntax, basically opening up almost any field of math you'd want to explore. We've just covered a bunch of symbols and rules. But why? Why does it have to be this specific? Why does this syntax matter so much? Well, it all boils down to one incredibly important idea: precision. You see, human language is full of shortcuts and context. We can understand nuance. But computers, they need absolute clarity. A strict syntax, like the one we've been learning, just gets rid of all the guesswork. It makes sure that the problem you think you're asking the computer to solve is the exact problem it's actually solving.
And that, right there, is the real magic. Learning this syntax is like getting a new superpower. It lets you hand off all the tedious, complicated number crunching to a machine, which frees you up to focus on the bigger picture, on solving the actual problem.
And that pretty much brings us to the end. You now have the fundamental grammar to speak the language of mathematics to a computer. So the only question left is, what are you going to ask it to do?